Okay, so hello and good evening, everybody. As chairman of the Hamburg Branch of the Royal Aeronautical Society, I welcome you all to tonight's lecture. Welcome to the sweet spot of meeting nice people, having good food and drinks, and of course, very good technology. So I'd like to introduce Dr. Jörg Peter Müller from, don't say Eurocopter, so from Airbus Helicopters. And he's responsible for the urban air mobility. He's managing director of the in Munich-based Urban Air Mobility GmbH. And he's an expert how we transport and fly in the future, I would say. I like to welcome, of course, our colleagues and friends from Autoflug, who hosted this Gerhard Sedimayr Lecture, this named lecture, in the 8th year tonight. Long-lasting series of success, I would say. And if I look around, I would say, you prove it already. Nearly 100 people tonight. Registered, so very good. I would say, Dr. Müller, the stage is yours. So we are listening and hanging at your lips.
Yeah, so thank you very much. It's a great honor and pleasure to be here. And if it has been successful in the past, then it's even more kind of a challenge to do something that's interesting. I think the subject in itself, it's really orientated versus the future of flying. It's a big subject, especially for us. It's a great pleasure to talk about it. I will give you a quick overview, because I think in general there's quite a lot of myth and fantasy about what urban air mobility can do and also cannot do. So I'll talk a bit about generally where we are standing at Airbus, what we are doing, what's our next steps, and then I'll dive a bit deeper into everything that's related to safety aspects, because we're talking about a new technology, a new business model, a new system of transport with all new challenges in terms of safety. And that's, I guess, the part where we also, in this context, can have a good discussion. I'm jumping over things quite a bit, so I'm trying to take a couple of shortcuts in order to squeeze it into the time frame we are having. But don't hesitate at the end to ask your questions or get back to me, so that we can elaborate on a bit deeper subjects. So, urban air mobility. Why are we at Airbus doing this? Why is it so interesting? And there is multiple aspects to that. Obviously, there is a societal need for efficient transport solutions. I mean, we've gone through the Alp Tunnel tonight. Everybody knows the challenges that are related to ground transport and to congestion. And what we are doing here is a complementary means of transport. It will not replace the Alp Tunnel. It will not replace a mass transit system. But it will provide an additional solution to people that value basically the time saving or the reliability that comes with flying. So there's one big aspect about societal needs, and it's not only about flying passengers. There's also other missions that we can do, and that can range from medical missions, not exactly a helicopter emergency medical mission, but transporting doctors, for example, to an accident site between hospitals, elements like that. It can also be for eco-friendly tourism, so flying over specific monuments without creating too much pollution visually and sound-wise. So there's a lot of aspects where urban air mobility, or what the eVTOLs in general, will find their market. The second pillar, and that's very, very important especially for a company like Airbus. So we are talking about electric flight. We are a precursor for everything that's related to local zero-emission flight. And we're developing the technologies that are necessary for that at a scale that's a kind of a four-seater size. So a scale that's relatively manageable in terms of technology. It's about kind of the order of magnitude of energy and power that you need here, like in a high performance car, electrical car. It's not yet the megawatts and so on that you will need for in the future. So it's a good step towards electrical flight also at greater scale. And therefore, the investment that we are doing here is building not only the knowledge in the brains, but also the technology bricks for the product range of such a diverse company as Airbus. And obviously, such a new means of transport is a business opportunity. So it's a way for us to develop a future business line that can kind of capture this new market and therefore also contribute to the prosperity of the group in the long run. So many important elements that make us invest into urban air mobility. Now let me start a bit on the technology side. It's not really all about technology, not only about technology, I come to that, but the question is always coming, why are we talking about urban air mobility now? Why not 30 years ago? Because 30 years ago, there were helicopters were existing, you could have taken off and landed vertically in cities and so on. So why now? And the main reason is the advancement of electrical propulsion technology, battery, energy storage, etc., that allow you now to build a vehicle that is relatively silent, economic, zero local emission, and that brings actually a solution that's economically viable and gets more competitive compared to ground transport. And now why are we doing eVTOLs? Why do we not just take a helicopter and put an electrical motor on it? This is because you can actually now, and that you can see on this slide, you can very much tailor your architecture of your airplane to the mission that you are looking for. So if you want to fly a more longer range, higher speed mission, then you put a wing on it. That makes it much more efficient in cruise flight. If you have a mission that is more like shorter hops in a city or just really close by, then you would rather do a multicopter. That's on the far right. And then you have different versions in between that allow you to adapt, go faster, go further, be simpler, be cheaper. And so out of this whole new design space that we are having here, the whole industry is now kind of thinking about what's the right configuration, what's the right solution for things. And yeah, we just had it today. There's about 700 different concepts out there in the industry now. It's 700 different projects that are trying to explore this space. And I think it's just realistic to say that nobody really has the answer of what these eVTOLs will really look like, but we are all taking our knowledge, the industry and ourselves, and trying to project into the future with our knowledge and what will be then the right eVTOL architecture, and I come to that now. But before showing you the future, I will just show you the current status. This is the CityAirbus that we are flying here, in this case in Manching in southern Germany. This is a vehicle that is 2.3 tons max takeoff weight, so it's the real scale, size, power, and so on of an eVTOL of the future. We are not reaching yet the performance in terms of range and speed that we would expect, but you can see that we are mastering such a configuration already today. So you have, What you have here is our very, very first generation of eVTOL. So it's basically a kind of a drone at the scale of a passenger transport system. And it has been designed with the idea of, well, first of all, starting with the simplest possible configuration, so multi-rotors. There's not much on it except for control, except the RPM control. Then you have a cabin that is already designed for easy access, egress, great visibility, to a certain level comfort already. It doesn't have a real cabin yet, but the shape and the form is built so that it's in there. We have taken the safety aspects into account that we knew about in 2015-16 when we started this project. And since then, a lot of things have evolved, and our knowledge has evolved very strongly. And on top of that, we have done a second vehicle that's called a Vahana. That was a different group in the United States, in the Silicon Valley, where we have our innovation center, A-Cubed. And this vehicle has been built at the exact opposite of the design space. So this one is now a vehicle with dual tilt wing. It has also 8 propellers. The wings change, or the aerodynamic configuration changes from vertical takeoff, tilting forward to horizontal flight. so it's very efficient in horizontal flight. But it requires, for example, variable pitch control of all the propellers, tilting mechanisms that are safety critical, so not easy to not easy to certify at the end. So a certain level of complexity with flight control, with control surfaces for forward flight and so on. And it has been designed for an equivalent of about 1 passenger. And I've seen the flight, this one as well, and it flew at the end. It flew 50 kilometers at about 100 knots, and that's a pretty impressive mission. And when you see and hear it, it was almost inaudible because in forward flight it was in this wing-borne configuration. So that experience gave us a lot of data on top of what I've described about the CityAirbus below. And based on that data, we have designed a new generation. So we call it very creatively CityAirbus NextGen, and that you can see on the right. So it's building on the bricks of having a wing. It's still trying to minimize the complexity of the vehicle in terms of transition and so on. It still has no moving surfaces. It's still only controlled by RPM control. And just because of the shape or kind of the configuration of the propellers, it's a bit difficult to see on this black screen, but you have 6 lifting propellers on the, let me just take the next slide, you see it perhaps a bit better. You have 6 lifting propellers on the wing, and you have 2 lift-push propellers at the back, so it takes off like a multicopter, basically, like the first generation of CityAirbus. And then it slightly tilts forward, and the tail, the 2 rotors, propellers at the tail, will create a forward thrust as well as a part of the lift, and so it will transition into forward flight. So there's nothing changing, there's nothing tilting or moving or whatsoever. It's basically only a kind of the attitude of the airplane moving into forward flight and getting back out of forward flight again. So this, with this architecture, we think that we can build a product, so meaning a real certifiable product. That's our target, our vision. That is a 4-seater. So at the beginning there will be 1 pilot plus 3 seats for 4 passengers. That's the initial aim. It will fly about 120 kilometers an hour at a range of about 80 kilometers. It will be almost inaudible again, especially in cruise flight. When you're in an urban area where you have some ambient noise, you will probably not be able to hear it. At takeoff and landing, yes, it will create a bit more noise. That's normal. The sound emissions there are more important because we are really in this totally propeller or rotor-based lift part of the flight envelope. So, but still, with that configuration, we think we can stay below what we usually have in the industry. The whole vehicle will be certified about the EASA, along the EASA special condition VTOL, and I'll talk quite a lot about it in the second part of the presentation. And this is kind of the European approach to it. FAA has rules as well, of course, for certifying this aircraft. Now, where are we standing at the moment? So we've done, in order to come to this configuration, quite a lot of studies and analyses. I've talked about the 2 vehicles, of course, that we have even flown, but there have been, if I turn left down, there have obviously been a lot of simulations, a lot of calculations, especially in terms of aerodynamics, aeromechanics. And last time I've asked them, they had about 31 million CPU hours consumed for the aerodynamics calculation. That's already a while ago. So probably they are at 50 million now. So an enormous amount of calculation, because the configuration in itself is relatively complex aerodynamically speaking. So you have the basic lifting surfaces, the wing, the fuselage, but then you have 8 propellers that change thrust dynamically, and you have to kind of analyze all the interactions and couplings that you have between the different areas of the flow field. So it's quite a lot of work to predict such a aerodynamic behavior of the vehicle. That's why we have also done wind tunnel tests, of course, in a clean configuration without propellers, but also in a configuration where we had propellers with motors on them, so that they are really turning and creating lift. So to calculate and measure all the aeromechanic coefficients that we are having. We have built full-scale propeller that we've put in the wind tunnel and measured it also through the full future flight envelope, because that's not trivial neither. You have kind of edgewise flow there in this vehicle, so the propellers will stay horizontally during forward flight. They will continue to turn. For some other propellers are at a slight angle that create the forward thrust and the lift. So this whole behavior of such a rotor has been analyzed, and on top of that, we have also measured the sound emission, optimized the design. Here you can see at the bottom right, you can see a 3-blade propeller. But there is other designs that we have checked, and we have had 9 propeller architectures that we have measured and optimized in that sense. And that's very important. And on the top right, and I'll go to that a little bit later in the talk as well. That's the flight control simulation. So that's in our flight control center in Marignan, where you have a pilot already in the loop who is flying this vehicle and developing, first of all, the man-machine interface. So how will this flight be steered? It will not be a kind of, you will not control the attitude of the vehicle, but you will control the trajectory. You tell the vehicle what it's supposed to do. You don't say, okay, nose down, bank angle or something like that. So that's a very different concept in terms of controlling the vehicle. And of course, this is a fully electronic flight control system, so the flight control laws are playing a fundamental role in the stability of this vehicle. So this is just to give a bit of an overview of the work that has flown into this design already. And this cannot be done alone, even for a big company. This is a broad approach with a lot of very strong partners, as far as I can tell. So obviously there's everything that's around structure, and we source quite a lot of components from outside. We have Spirit in Belfast, for example, for the wing. So they are specialized in wing design, let's say in a smaller scale than what you would say have on an Airbus wing, but exactly what we need. We use Thales and Diehl Aerospace for the flight control system. And I'll come to that. It is a dissimilar, redundant flight control system with 2 different types of flight controllers, a primary one or 3 primary ones and a secondary one that can ensure that we have dissimilarity and redundancy during the whole flight. We are using US company Magic All for the motors. They have a strong competence in eVTOLs already. We used them already for the Vahana before, and on drones. So they are industrializing electrical motors for these kind of applications already today. We're using 2 smaller companies that are more like from the high-performance sports car part that are doing, for example, the rear structure there. And they are doing the design and the manufacturing with also principle, and then that's interesting for us, that they get from the automotive industry, in this case, from the Formula 1 racing industry. So we are trying to get kind of different types of companies with different approaches and new and different ideas into our system, ranging from large, well-known companies to also smaller ones that can bring a different approach, so that we learn as much as we can out of this prototype phase that we are currently in. So this vehicle will be flying in. So this vehicle, the components are currently in the detailed design phase. So we're going through that process. The components will come next year. We'll assemble them and then test fly the vehicle, and take obviously the amount of time it takes to understand fully this configuration and the technology of the different systems and the architecture in itself. Perhaps one thing I missed to say is that we are using batteries. That's another fundamental part. We are building them in-house. That's why you don't see it on the slide. We're building them in-house in our Airbus Defence and Space site in Toulouse, where they did already batteries for the previous vehicles, and doing that also for space application launches, satellites and things like that. And they have a capability of developing batteries. And and there will be other things that will need to come, like interiors, for example, and we need a strong support for that, of course. So that's about where we're standing on the vehicle. The vehicle itself is obviously one thing, but in principle, I wanted to show a second video, which is just about the test house. It's just because we have done it a few days or weeks ago. We have inaugurated the test house, and there was supposed to be a video that doesn't show, but in principle, it's obviously a lot of things that need to happen in parallel. The technical development, the whole testing concept to ensure that what we are doing here is really sound and safe. And then it brings me as well to the ecosystem view. And that's the second very important part. Yes, the technology is important. We are getting there now with the maturity of propulsion technology, etc. But such a vehicle will not be very effective if you do not integrate it into a transport system. So obviously, maintenance, operations, and so on, we know that from our industry. We also know that you need infrastructure. And today you have large infrastructure, airports, basically for air transport that you need. But if we want to deliver a meaningful service, then we also need to have infrastructure there where the passenger wants to go, or close to the final destination of the passengers. And that's not trivial, especially in European cities where you have very densely populated cities that have not much space for these kind of things. And it only makes sense if you fly to some place, if you then have to take a cab for another 20 minutes or something to get to your final destination, you lose basically a bit the advantage that you get from flying in the first place. So infrastructure at strategic location is key, and this infrastructure needs to be well utilized and profitable, so that it also kind of makes sense in terms of an investment case. So that's an important enabler for air mobility. Air traffic management is another very, very important point. You need to operate these vehicles, ultimately in non-segregated airspace, together with all other kind of participants in flight and in the airspace. So you want to have a helicopter mission, whatever, emergency medical service mission, you will have drones, you will have flying taxis, you will have around airports and over cities, obviously the commercial flights. All these kind of things need to work together. So the whole air traffic management part is super fundamental to make this efficient and safe again. And you need to deliver that service to a final customer. So you need to provide some integrated mobility experience that allows him to say, okay, whatever his constraints are, speed, budget, reliability, comfort, perhaps the pleasure of flying and seeing a city from above, whatever he wants, you need to give him a tailored mission. Or provide him a kind of a tailored solution that is comprised of a flying part, but perhaps also of a ground transport part, and of a whatever improved pickup at the airport, or a kind of a safety clearance, security clearance that he gets that makes it efficient. And you need to provide that to the passengers in an optimized and obviously connected electronic way. For that one, I wanted just to explain very shortly that we had actually, before the pandemic, operated a service that we called VOOM. That was using helicopters. That's what's existing today. And we started operations in Sao Paulo, in Brazil, but also in Mexico City, and at the end, even in the San Francisco Bay Area. And there you could actually book a flight with a button, basically, with the app that we had there. We had about 120,000 users that we are registering for the website, and about 15,000 passengers that we have transported. And out of that, we also got quite a lot of experience. We talked today about luggage or expectations in terms of what does somebody who wants to go to the airport, what does he take with him, or what kind of profiles do we attract most? What kind of travelers do we attract most? And things like that. That gives us quite a good view as well of what this market will most probably develop towards. So, and that again then is important for the design and the performance requirements that you specify for such a vehicle design. But again, all this is a projection now. This whole market needs to develop, needs to materialize, and then we can talk again in 10 years and see how the predictions work and how things actually really develop. And to not wait 10 years, what we are doing today is we are working with different partners throughout the industry on different aspects. So I've just taken 3 examples. One is a helicopter operator, THC, that wants to build a bridge between today's helicopter operations towards a greener, more sustainable operation, and then all the way to electrical flight. What we are doing with them now is to develop sustainable aviation fuel operations for helicopters, so reducing their emissions already immediately, basically, already today with the technology that's in the making, and then it will then it will develop into eVTOL operations in the country. So we have one operator like that. We are having, top right, signed an agreement with ITA in Italy. So this one is now more about integrating our operations with airline operations and to see how the business case looks like, how the passenger experience looks like, and how these eVTOLs can actually add value to commercial operations, commercial airline operations. And on the bottom left, this is an initiative that we are running in the Bavaria region, so basically around Manching, Ingolstadt, Munich, with about 30 partners, where we actually developing bricks and developing kind of minimum viable products, kind of the first proof of concepts, if you wish, for the air traffic management element of it. And we're doing, for example, with Tronic, which is again a subsidiary of Deutsche Telekom and Deutsche Flugsicherung, as an example. Or infrastructure, where we're working, for example, with the Munich airport, with Deutsche Bahn, and a lot of local companies as well. And that allows us to provide such first bricks of this operational environment, where we can test, first of all, that all this technology works, bring our eVTOLs, gain some experience, and use this knowledge then to roll it out for future use cases wherever they will be. So that's a bit of the overview around partnerships. Let me say it again, no single company will ever be able to develop this whole system that is needed here. Good, and that brings me to the second part of the talk, which will be now focusing around safety. So you can imagine that we are flying with large numbers, or we're projecting large numbers of flying taxis over the cities. But let me start with a little bit of context, and I like this very much, this chart, because it's very telling. This is the safety statistics of commercial jets. Yeah? So if you look at the bottom left, or let's take the top right, you have the gray, that's the growth of air traffic. Yeah? And the bars, the black bars, are basically the fatal accidents that you have over time. And you can see that despite a tremendous growth, this has been steadily improving. And if you now divide the two numbers, you will get to the accident rate, that's the bottom left. And we came from about 10 accidents per million flights to about 0.04. That's a 250 times improvement over the years. And that's, of course, because this was a collective effort. This is about a very strong safety culture. This is about a very strong technological progress. Yeah? And it's about industry regulators and so on working together in making that happen. And now the expectation, or the absolute must, is for us to have the safety levels of commercial aviation, because nobody will take a transatlantic flight and then get into an air taxi that's less safe. So we need to achieve what we have achieved over 50 years in the commercial airplane industry from day one on. And that's a bit the tough part of the story. Now, a little bit of technology, because this is a strong driver here, of course. This is the different generations of commercial jets, and we are starting at the top left. In the early days of jets, you had relatively manual flight controls, analogous instruments, etc., and not much support for the pilot. So you had 4 or 5 kind of crew on board that were controlling the flight and ensuring its safety. And at one point in time, you came to flight control computers that started to take some functions of the workload of the pilot, so a bit of auto throttle management of the technical systems, the engines and so on. And here we are about in the range of the A300 early days, where you had about 3 flight engineers still on board, but you had about 3 flight crew. And then you started to have more and more automated systems, so 2-man cockpit. Airbus, from our side, it would be the A310, A300, 600, A310, where you actually could reduce the crew to 2, and you had much more systems to support them, until all the way to the fly-by-wire system that was coming at the end of the 80s on the A320, that now even has functions like flight envelope protection, that then actually ensures or prevents accidents from happening. And when you look at the middle graph, you can see how this technology progress has actually improved the safety levels. This is again the accident rate is hull losses, so not only fatal accidents, but still you can see how significantly this has improved the situation. And here again, we are on a track and a challenge here, and the next generation will be better, and we need to be at this level or better with the technology we're coming about. And that's not an easy one. When you now look of what that means, now we're doing just a bit of math for eVTOLs. I took a market projection from the public. So in this case, it's Roland Berger numbers that has projected on how the eVTOL industry will develop. This doesn't mean that we are kind of saying this is not the business case for urban air mobility, but it's a publicly accepted representation. And it says that, it multiplies by 10 the number of eVTOLs flying every 10 years roughly. And you come to the numbers that you see here from a few in 2025 to about 16,000 in 2040 and to about 160,000 in 2050. Okay, that's far out. Okay, it's a tough projection, but still. When you do now simple math and you would achieve the safety levels that you achieve with commercial aviation today after 50, 60 years of flying jets, then you would actually start to generate, just by statistics, you would generally start to have accidents in the future. So the culture or the focus on safety for such an industry is just for mathematical reasons already primordial. So this is about what I wanted to say here. But let's look a bit deeper where the accidents come from. So this is again a large commercial jets. Here you have the primary case of the accident. It's generally an accident is generally concatenation of different unfortunate events. It's rarely just one single event or failure. And then there's generally a primary cause and some secondary ones. And what you can see here is that, let's perhaps start from the top right with the smaller ones. You have kind of air traffic management, weather, operations, things like that can happen, some difficult to classify. And then the larger block, the orange one, is around technical failure of the aircraft. So this is the one that you're working on in the design and the certification of the aircraft. And then there's 56% that are related to crew errors, human factors and things like that. Now, the statistics are a bit tricky because there's also many cases that are not captured here where the pilot actually saved the aircraft. So the Hudson River landing of Sully was kind of the most famous one, so that you cannot really see here. So it's not just that there is a negative message in this, but the effect of having kind of human factors in this whole system makes us take a very holistic approach. It's not only about safety of the vehicle. So what we are doing here now is we are attacking the different areas from different angles. Let me start on the top left. So there's a lot around air traffic management and use space. We call it use space. That's kind of the airspace, the lower airspace over cities, where the drones and flying taxis and so on evolve in. And there's a European EASA-driven initiative of integrating, kind of installing such a use space so that drone operations, air taxi operations and so on can happen safely and efficiently. So we are actively developing with one of our centers in Europe and in the US specific services for managing the aircraft. So what you really need to track, follow, authorize the vehicles to fly. We are also having what we call a digital twin of the airspace. That means a kind of a simulation of what the airspace looks like, so that you can actually test what different types of regulatory or procedural directions, what kind of effect it has on safety and on efficiency of the airspace, and therefore the whole operations. And we are using that entity as well to kind of provide insights to Airbus at larger scale of how these vehicles will operate together in the future, especially in a non-segregated part of way of the airspace. So that's a big chunk of work we are doing in our ATM UTM group. We are working quite a lot on autonomy, so that's the bottom left. Autonomy is mainly dealing with human factors of piloting and so on. So what we are trying to do is to provide more pilot support functions of all kinds, situational awareness and reducing the workload of the pilots, always with the objective to minimize all kind of potential errors. But also we need a large number of pilots, so also to reduce operating or pilot costs, kind of make it easier and simpler to fly the vehicles. You can also better optimize the trajectory if you automate it better, save energy with that, things like that. So pilot workload is very, very important in the safety actually of the flight operations itself. Then on the bottom right, you see everything that's related to the vehicle safety, and I dive into that a bit further. This is the famous special condition VTOL that EASA has issued. And the top right, everything related to operations. What's, for example, one important element is kind of a more condition-based maintenance concept, for example. So you don't have fixed intervals, but you do actually your maintenance according to the needs of the vehicle and the evolution and the usage of the vehicle. And different kind of operational procedures that you use to improve the flight conditions. So again, with the certification and with the certification part, safety part, you only touch about the 17% on the bottom right. But still, this is fundamental in order to make safe operations possible. Now, that's the tough one, the tough part, and the kind of the, let's say, adventure in urban air mobility. So what we are doing here, we are developing regulations and technology at the same time, and business models on top of that, and infrastructure and so on. Because all of that needs to converge here, represented at the top right. And once everything is there, the regulatory environment and the technology, only then we can really start the operations as it should be. And there's many aspects. There's basically, if there's four main aspects here, that's everything a bit similar to what I said before. You see it on the top left. Everything that's related to supporting the pilot with artificial intelligence or reducing workload. Autonomy, it's called here. Everything that's related to use space. Then everything that's more the operations and maintenance concepts. And on the bottom right, everything that's more related to the vehicle itself. And all these elements, they have different working streams together with the regulatory bodies, the standardization bodies, and industry working groups in order to come to this top right. If you take just the example of the regulations, so the certification regulations, the SC-VTOL, you will see that this is this part here. You can see that the EASA has already issued in 2018 the first regulatory framework for comments, which is fantastic because that enables basically the industry to have a frame and a target that they are working towards. So it was published in 2018 for comments, and then it became the special condition VTOL. And with that, they have also issued shortly later the applicable means of compliance. At least the first two batches, the first two important ones. That means the MOCs that are the way you develop and you qualify, you demonstrate that you achieve actually the certification requirements. So the means of compliance help you in doing that, because this is something that has been already tested, proven, approved in how you design your vehicle. And you can see now we are roughly at Mach 3. This is the third batch of applicable means of compliance. Here's a lot about batteries, for example, and operating electrical flight in this part, which is actually a tough one as well. Now you can look at all the different areas here. We'll not do that now, but just to show you that there's a lot of moving parts in this, from battery technology to regulations to the future market needs. And that makes it, on one side, very interesting, very exciting, but on the other side, a bit uncertain as well. So, certification requirements, because this is the kind of a top subject. SC-VTOL is a performance-based regulation, so it's not prescriptive as it was before on the certification standards that we're using from let's say 2729, CS 2729 for helicopters, for example. So it's performance-based, and it depends what kind of safety standards you need to reach, depends on the mission and the performance that you get. So let's perhaps not go too much into detail, but there is basically two categories. There's a basic category, which is for non-commercial flights over non-congested area, not densely populated areas. And there is the enhanced category, which is actually for commercial operations and or over densely populated areas. So flying taxi, by definition, urban, densely populated, commercial operations, so it's the enhanced category. For the enhanced category, you need to achieve a certain level of safety, so meaning the number of failures per flight hour. And that's this 10 to the minus something that you can see here. And let's perhaps take only this line here. Now, there's, you need to prove that your system is at 10 to the minus 3, so 1 in 1,000. It is capable or is not generating minor errors. Some minor errors are just, or minor hazards that are just actually increasing the pilot workload and kind of reducing a bit the safety margins, but are not difficult forever for the airplane. The remote one, the major ones are okay, increasing significantly the pilot workload, but still manageable. Then the hazardous ones, now it's getting critical, and the critical ones means actually that you do not reach your mission goal. In this case already, it's considered a critical event if you do not reach your final destination, your mission destination that you had planned before. And the target here is 10 to the minus 9, so catastrophic failures per flight hour. And this is exactly, or it's basically the safety level that you have on a large commercial airplane. That means we, with our little eVTOL of 2-something tons, we need to reach the same safety level as an Airbus A350 out there. And in particular, we are fly-by-wire aircraft, so we have systems like that. We have battery energy storage and all that kind of things, and we need to reach that level. That's a pretty tough one. Another one that we get in the enhanced category is actually the continued safe flight and landing. So obviously, we cannot emergency land in a densely populated area. That's not acceptable. So it prescribes that if in every failure scenario, of if you have a single failure, you need to be able to complete your mission or complete a flight and land safely. This is different as well from helicopter operations. And if you take the basic category just as an example, in this case you are allowed to do a controlled emergency landing. So that's acceptable, but not for commercial operations in this enhanced category. So a tough one for us to crack. Now, let me talk about 3 key and novel aspects that we have in there. So the first one is around the lift and thrust units, so basically the propellers, the motors and the propellers that are now an integral part of the flight control system. So you cannot segregate as you have it more on more traditional airplanes, where you have a flight control system with surface and so on, and the thrust management system for the motor. So it's integrated because the 2 functions are now basically the same. So you have only one integrated system in that sense. Yeah? And obviously the whole flight control system, motor controls and so on, needs to be all according to this functional DAL levels. They were on the first slide. This is kind of the development assurance level. It's kind of the rigor, the process that you have to follow in order to qualify your system, your function, your software. There you can see it very well. It prescribes how you track, monitor, how you track your software and how you ensure that it's error-free. So that's the design or the development assurance level. But anyway, it needs to be developed. Everything needs to be developed according to the highest DAL level, meaning like a critical system on an airplane, on a large commercial airplane. And and you have to actually see the safety objectives at aircraft level. In this sense, you cannot only say, okay, my motors or whatever are at this level of safety. No, you need to really look at it at an aircraft level. And what you do as well is you derate to some extent. So meaning you build systems that have some margin in it. So flight control computer that has more computational power than is really needed, or a bit more bandwidth in these areas, so that you have a bit of margin in there in the system. Should the logic, the software, the algorithms evolve at one point in time, but also to ensure that you do not have an overload of the critical systems. You do a bit of more redundancy, and you kind of qualify how these safety measures are looking like. The second thing that you have to do is actually, like for highly integrated systems, you have to go through a V&V process that is tracking your requirements and ensuring that everything's according to those. I'll come to that. And also I'll talk a little bit about the failure criteria for structures, which is also a bit of a different one here. So starting with the first one, the lift thrust unit. So here's a simple scheme of how this interaction looks like with the flight control computers on the right, and here the electrical propulsion system on the left. So okay, we have a distributed electrical propulsion system, which is obviously very favorable in terms of redundancy. So we have 8 propellers in this case, with a certain architecture for the batteries, multiple batteries, and power distribution. We have identical motors, or lift, we call them LTUs, sorry for the abbreviation, lift thrust unit, basically the propeller and the motors that provide the lift and the thrust. They are same, basically the same, and what you have to do in this case, the LTUs in themselves, the controller and the architecture of it, needs to be with a redundant architecture already inside these components. And this is important because you do not want to have kind of common mode failures. If you have the same design everywhere and there's a mistake and you don't have any redundancy or dissimilarity in there, you will have troubles on multiple systems and that you cannot deal with. So in our case, there is no tilting mechanisms and so on involved, so the configuration itself stays the same. That makes it a bit simpler. Perhaps one word about the batteries. Yeah, there is multiple battery packs in there, and obviously we are tolerant to a loss of a battery pack. And there is a lot of challenges, obviously, to the battery part in terms of storing such a big quantity of energy. We're talking about the same size of such a high-performance car, roughly 100 kilowatt hours of energy, and to ensure that thermal runaway and also the crash elements and so on are well mastered. So that's a tough one. So the regulations or the means of compliance are currently in a consultation phase. There's probably something like there will be 2 cells of a battery pack or thermal runaway of 2 cells in a battery module need to be contained as an example. But there's actually these kinds of means of compliance coming out soon. Good. And on the right-hand side, the flight control system. So here we are very lucky as well because we are having quite a lot of experience in flight control systems. Yes, you see them on large commercial airplanes, but we also have on some helicopters, and we are using that experience together with 2 very strong suppliers that I mentioned earlier. And the same applies here, like to a commercial airplane. Yeah, we have full fly-by-wire, we have flight envelope protection, and we have obviously assistance to the pilot to the right level. Again, dissimilar and redundant, and we've pushed it that far that we even have 2 suppliers of flight control computers, whereas we are doing in-house the architecture of the flight control system and the software, the algorithms. So this is kind of to deal with this first element of integrated lift, thrust, and controls, flight controls. The second one, again to this V&V process, I guess the principle, the basic principle is the same, like in the aerospace industry in general. You have requirements, performance and safety requirements. You manage the requirements at the aircraft level. You break them down to system, subsystem, component level, all the way to manufacturing, and then you basically develop your elements, your components, your parts. You build them, and then you assemble them part by part, or kind of level by level, from subsystems to systems to the aircraft, and at each time you test it. And that's the part that I wanted to say with the test house. So we are investing heavily into that one as well, so that we have a facility where we can actually do the tests throughout the V&V cycle, all the way to the full aircraft sitting in a hangar with the propellers turning, generating thrust. And we can do that in stable conditions before we send it out and really fly it. So the component tests are already running as of today. We've received the first components for the ground tests, or for the bench tests. So we are testing motors, flight controls, and so on already. And we get step by step over the year and over next year to have everything together and in the test house. Okay, this testing approach is also seconded by a very strong modelization simulation capability, and that's about what I mentioned earlier around aeromechanics, aerodynamics, but as well, I mean, generally all the different aspects of the operational behavior of the vehicle, handling qualities through the full flight envelope, etc. The piloting concept that you can do also offline. You don't need to. You will not wait until you have the vehicle there. You do that in a simulation. I showed a little picture earlier. Yeah, and all that coming together will ensure that we actually reach the safety and performance targets that we have specified at the beginning. It's a typical approach, but you need this kind of approach in order to reach in such a complex system of systems to reach the maturity that you expect, even from a prototype. Now, the last part that I wanted to go into a little bit further is around structures. So here again, there is a specific requirement that means that no single failure can lead to a catastrophic event in such a design. That means that unlike traditional vehicles, so let's take a helicopter where you have critical parts, so one single part that cannot break, and you ensure the kind of you ensure the safety of that part by many different means. That's something we're doing in the helicopter industry normally. Here, you have to actually provide a kind of a fail-safe design, where even if there is one component, in whatever component breaking or dysfunctioning, the whole system needs to be able to recover and continue safe flight to recover this situation. So one element of doing this that's described in the means of compliance is to have multiple load path type structures. We are doing this in large planes as well, of course, but generally you have multiple load paths. So if one is breaking, the other takes over. You inspect, you see that there is a condition that there was a failure, repair the other part and the part that was failing, and that's about the procedure. So, and with that, you are able to ensure these safety levels. The no critical part is tough in a rotating system. Yeah? You can imagine this multiple load path on a structure, on a wing, or on a fuselage, etc. On a rotating part, it's tough because you have to ensure this kind of mechanical behavior or complexity that you actually always have a second path or way of controlling or whatsoever that ensures that it's not failing. If you look at a couple of very specific points, I listed a couple of here, bird impact, especially if you have a flock of birds and they hit the multiple rotors at the same time, so things like that. That's not really trivial to manage. Yeah? So high energy fragments, another very tough one. When you look at a propeller plane and you see the propeller plane, you have the propellers, and in the plane you have a protection on the fuselage if ever there's something going wrong with your propellers. Now what we have is see all the propellers here. We have 8 propellers in all kind of orientations. You cannot shield the fuselage or something like that. So you need to find different ways of ensuring that there's no fragments detaching from the propellers and hitting any critical part or the cabin or a passenger or so on the vehicle. And you can do that as well, again, with the architecture and the different design or the different design principles that you apply to a blade, so that you always have a second load part. There is no fragments, high energy fragments developing and projected. So that's a very important one. Fire protection, thermal runaway of batteries and things like that. Okay, we do not have liquids, burnable liquids on board. That's an advantage, but lithium-ion batteries are also a tough one to manage, as we all know, I guess, especially also from the aerospace industry. So there was a lot of experience on that. It's a tough one, and so protecting the aircraft itself from that is a big novelty, let's say. That's about the overview of the different critical points, but just perhaps a couple of further thoughts. Things that we are working on at the moment. If you take a commercial plane, then you will have a kind of a 20 minutes. There's one 20-minute requirement that beyond your mission, you need to have 20 more minutes of flight time so that you can, whatever happens. Okay, our mission is only 15 minutes. So if we have, we apply the regulation as it would be now, it would just not be doable. So that's already a challenge. How do you deal with that? Or how do you adapt this requirement that has proven its worth over the years? And we have seen the graphs at the beginning to what that has led in safety. How you take these partially really kind of old regulations that have been developed decades ago, and to adapt them now to our case without impacting, harming kind of the safety levels that you want to achieve. Another example, if you take today's approach, you would have almost AFR type operations. That means you have your mission fuel or mission energy. In this case, it's electrical energy. Then you have to have the fuel for reaching an alternate or two alternates, even landing spots. Then you have to have a safety margin of 5% for bad weather and other conditions. And then you have another general safety. If you accumulate all these safety margins for a mission like ours, then again, this thing becomes very, very difficult to build, to have that energy on board. These are just a couple of examples where the industry, where the regulators, also with the support of the different actors, is actually working, and where it requires really a deep thinking on how to do that in the future. Yeah, and with that, I would say we'll end the talk. Many thanks for your interest. As you have seen, it's a very exciting and challenging subject, but also which has great potential and it's great fun to work on. And especially with a great team and a great support, it's just fantastic to work on the future of aviation. And yeah, I'm more than happy to answer questions now.